Is it audible? Hello.
Yes, sir.
Okay. So good afternoon to one and all. The morning class we have discussed about some resistance temperature coefficient and classifications of different transducers and definitions of different transducers we have discussed. And now we'll go for the electrical transducers only here. So some three transducers they have mentioned in your syllabus, that is resistance temperature detector, LVDT and RVDT here now, linear variable differential transformer and a rotational variable differential transformer, that is RVDT we are going to call that one. So in the morning we have discussed about the transducers, so many transducers we have discussed. In that one, I told to remember only about electrical transducers. Can anyone define electrical transducer? Define electrical transducer.
It converts mechanical quantity into electrical quantity.
Mechanical quantity into
Electrical one.
Electrical quantity.
it is not clear. Mechanical to
Electrical quantity.
very good. So the electrical transducer, it is a device which converts physical quantity into electrical quantity or mechanical quantity into electrical quantity. So the output we are getting electrical quantity, then we are going to call that one as electrical transducers. We are going to call that one as a electrical transducers. So number 2 and 18. Okay, so in that one, we are going to discuss about three transducers. We are going to discuss RTD, LVDT, and RVDT. See, the resistance temperature detector, that is called RTD, we are going to call that. The industries, we are going to use this type of devices here now. So for that reason only the name came here now, industrial platinum resistance thermometer or bridge circuit here now, second one. See, we have discussed the Wilson bridge, Kelvin double bridge, Maxwell bridge, Hayes bridge, Anderson bridge, DeSotti bridge, Searing bridge, and all the bridges here. So according to that, we have to make the, if the bridge is unbalanced, the galvanometer is going to detect value. So we have, by varying the other resistances, we can make that one as bridge into balance condition. We have already discussed that things. Okay, that one you know that one. So this resistance temperature detector, what it will do here, for the increasing temperature, the resistance will vary or not. That one it is going to sense here. So the thermometer, we are going to call that one. The thermometer, what it will do, it is going to check the temperature in the form of resistance. We are going to measure that one. The output is in the form of resistance, but the input is temperature here. Now we are going to temperature, resistance temperature detector here now. Okay, see, this is the actual product. The output of this product we have means what is that one? The picture of the product here now. So it has two connecting leads are there. This one I'll show here. This is one connecting lead and another one it is connected to the bridge circuit here now. Okay, connecting leads we are going to call this one and this one. See here, mounting threads are there here. Inside that we can fix a screw by using the screw like this. We can fix this one into any boards or any equipment. We can fix that one where we are measuring the transformer. So that one here, the mounting threads are there here. Mounting threads, this whatever the lines are there, that is mounting threads we are going to call that one. Okay, this is a sheath which is protected by the whatever the leads and the element here now, sensing element, the sheath we are using here now. For the supporting purpose of lead support we have used here now, lead support we are going to call. And whatever this dark area it is there, it is going to indicate that that is a sensing element. The sensing element we are using platinum materials we are going to use here. The platinum material we are using here now. We are using a platinum material. This is the construction of the resistance temperature coefficient, the detector here. Resistance temperature detector here. So the operating principle, how we are going to operate here now. So here R1 fixed resistance, R3, R2. We are using R1, R2, R3, R4 and R5. We have used some 5 resistances we have used. In this one, the sensing element here, it is going to sense the temperature here. No? We are going to use, this is the sensing element resistance, that is called RS we are using here. No? The sensing element resistance RS we are using here. If the temperature is varying, we have to give the supply to this one. We are giving the supply. Then what will happen if the temperature is varying? Then the resistance of the sensing element resistance will vary. So the bridge is said to be unbalanced now. This resistance is vary, then the bridge is unbalanced. Bridge will occurs over there here now. So by varying the other bridge resistance value, we can bring the bridge into balanced condition, and by applying the formula of the balanced condition here now, RS, we can calculate that one. We can calculate the RS value. By making the bridge balance, we'll get the value of R1, we'll get the value of R2, R3, R4, R5. So we can calculate the RS value, we can calculate that one. So that is the construction, and based on the bridge circuit, we are calculating the value of the resistance here. We are going to calculate the value of resistance here. This is with the diagram I have explained. Some points we have written, everything I will read and I will explain once again. So the definition, actually it is now the resistance temperature detector, also known as the resistance thermometer, we are going to call that one. The resistance temperature detector is nothing but RTD. RTD we are going to call as, and also called as resistance thermometer we are going to call. It is an electronic device, which one we are going to use to determine the temperature by measuring the resistance of electrical wire here. So in the bridge circuit, we are measuring the resistance, but the input we have given as temperature. So that temperature in the form of electrical quantity or resistance we are going to measure here now. So the construction part. So the construction and working of the RTD here now. First, the resistance of conductor changes with change in temperature. So temperature changed means the resistance is going to change here. That is the principle we understood that one. Resistance temperature detector, what it is now. If the temperature is changed, it is going to detect and it is going to change the value of resistance. It is going to change the value of resistance. It is going to change here. As per the figure, whatever I have shown, wherever the construction is there, I will use this. Leave that one. So in the construction of this diagram, I have told already, this is connecting leads are there inside that one. The upper side of the, it is protected by a sheath, and it is lead supports are there inside that connecting leads. The sensing element we have used, and total overall we are using a mounting threads to mount the product. So same thing they have written here now. Above figure, whatever we shown the figure, the construction of platinum resistance thermometer. The sensing material we are using as a platinum material we are using. So for that reason, the construction platinum resistance thermometer, the name came here now, in which platinum material is used as a sensing element here now. So the material used is platinum material. So for that reason, we are using as a platinum resistance thermometer. We are naming that one here. So the thermometer is generally a long spring, like a safe enclosed in metal sheath here. Now in the metal, we have used a long spring, like we are using that one here. So here the leads are there here. Now it is a long leads are connected here now, and the platinum material is added here. Now it is like a long spring only, they are telling that one here now. Then this is inserted in a medium whose temperature to be measured. Where the temperature we have to measure, in that place we have to keep that one, we have to insert that one here. Mounting threads are provided for perfect installation of the instrument. So mounting threads we have provided, we can fix at particular place by inserting the whole material we can insert, and we can fix that one on a board, or if wherever the requirement is there, we can insert that one. Okay, for that reason they have mentioned they have given the mounting threads are provided for the perfect installation of thermometer here. So now we'll go for the bridge circuit here. Now the bridge consists of sensing element, that is called sensing resistance, that is called RS, and R1, R2, R3 are the other resistances as an arm of the bridge here. Now these two are the standard resistance we are using here. Now the R4 and R5 are the resistances of leads connected to the sending element here. Now this resistance, lead resistance is R4 we have used, another lead resistance we have used R5 here. Now by varying RS, R4, R5, we can bring the bridge into balance condition and we can measure the RS value here now. So due to change in temperature, suppose temperature changed, then what will happen? The resistance RS, that is nothing but sensing element, inside we have used, that is platinum material, it is also going to changes that one. Temperature change means the sensing element will also changes and the bridge will become unbalanced. So bridge is unbalanced, then the galvanometer, the current will start to flow in the galvanometer. It is going to deflect some value. It is going to deflect some value. So the galvanometer shows the deflection, which can be calibrated. Calibrated means we can get the value to give the suitable temperature scale here. Now by varying that one, other resistances, we can bring the bridge into balance condition and we can measure the value of resistances, and that one we are going to convert it into, or that is proportional value to the temperature we are going to call that one. So the variation of resistance of the metal with the variation of temperature is given as, jaisa resistance will increases, like that the temperature will increase, with that increasing temperature the resistance will also changes. So the equation for that variation of resistance with respect to temperature is given as, this is change in resistance or resistance at temperature T degree Celsius, resistance at temperature 0 degree Celsius, 1 plus T minus T naught plus B minus T, beta into T minus T naught we are going to use. Here one thing they have missed here, no, this formula is wrong. Here we have to add alpha here. So for the large value of change in the temperature and resistance, we are going to use like this alpha, beta, gamma, we can use that other values also. So those are the constant we are going to call that one, alpha, beta, gamma. Okay, these all the things we can use as constants. We are going to use that one here now. So here this equation we are going to use where RT is and R naught are the, first I will tell the RT. This RT is nothing but resistance at temperature T degree Celsius, how much resistance is there, and resistance at 0 degree Celsius or T naught degree Celsius, that is R naught we are going to use. So T degree Celsius and T naught degree Celsius, T minus T naught, T is the final value, T naught is the initial value. We are going to calculate here by using this one, net change in the temperature we are going to get. Similarly, if we R naught, you multiply that one, you send into here RT minus R naught, it will give the value of change of resistance here. Now, so we can compare that and we will get that value here now. That is they are telling here now. So RT is the resistance at T degree Celsius, R naught is the resistance at T naught degree Celsius. Alpha and beta, this alpha, where it went, alpha and beta are the constants, depends on the metal value here now. Based on the metal value, we have used some constants here now. For small change of temperature here now, for the small change, the formula is limited to this one only up to alpha only. Here, up to alpha for the small value of change here. Here we have to use alpha here. This is the value or resistance, the formula we are going to use here now. So you can compare with RTC. RTC का formula क्या लिखा था मैंने? Anyone can you tell me? What was the formula I was written for the RTC? Anyone can you tell me? Yes. कोई भी बोल सकते हैं ऐसा कुछ नहीं. Any one person. सर क्यों पूछते सर ऐसे बोलते? So in the RTC we have written as total R equal to R reference. Yes or no? open bracket 1 plus alpha t minus t reference. यही फॉर्मूला लिखा था हमने. Yes or no?
Yes, sir.
So is there any difference between this formula and this formula? Anyone can you tell me? ये दोनों फॉर्मूला में डिफरेंस है क्या कुछ? What is that difference? You tell me. Is there any difference in these two formula? If yes, then tell the difference. If no, we will continue. I want the answers. Yes? Any one of you? Sir, पूछो मत बोल रहे. Okay. Here RT we are using here. No, instead of RT we are use R here. This is R. And here R naught is nothing but 0. At the initial value we are using. The reference value we are going to consider here now. The resistance at T reference here now. And this R reference. R is at the temperature T here now. There is no difference between these two values or formulas here now. So resistance temperature detect, it is going to detect here now. And that is coefficient, that is called alpha. We were going to measure, that is called RTC over there. By using the same formula, we have calculated the alpha formula. Alpha formula calculation किया था ना? RT minus R reference. RT minus R reference divided by R reference into T minus T naught or T reference. So to calculate the alpha value, we have derived this formula. Okay, so here the detector RTD we are to measure the for small value of resistance temperature detector, we are using this formula here now. There is no much difference between that RTC and RTD here now. So now I told in the RTC there are two methods. One is positive temperature coefficient and second one is negative temperature coefficient. Okay, positive temperature coefficient and negative temperature coefficient we have discussed in the morning class. Okay, now here resistance temperature characteristics are there. We have considered three material. One is nickel, another one is copper, another one is platinum here. So is there any difference between this by seeing this curve? A curve, A curve, A curve. डिफरेंस दिख रहा है क्या? कोई तो बोल सकते. Is there any difference? Roll number 1, B division. कुछ difference है क्या? This curve and this curve. Is there any difference? Roll number 1, Shobna. Hello. Yes, madam, you have to unmute. This is last call. One is absent. Next, roll number 4, Aishwarya. एक क्लास absent होना है और एक मार्क्स कम हो जाते हैं आईसी में टर्म वर्क में. Remember that one. Aishwarya Gaikwad. Roll number 4. Roll number 5.
Yes, sir.
हाँ, कुछ difference है क्या इधर? From this
Yes, sir.
material, copper material, platinum material. Yes, difference is there.
Yes, sir.
Okay, very good. Yes, enough. That's it. Answer is enough from you. Next, roll number 8.
Yes, sir.
हाँ, क्या difference है बोलो मैडम इधर? What is the difference here now? You are observing.
जो कर्व है वो
जो कर्व है वो Okay. Roll number 9. Kartika. Roll number 9.
Yes, sir.
बोलो मैडम क्या डिफरेंस है? Okay, leave that one. See here, I will consider only nickel. I will consider here now. Where I have to draw, I will draw here now. See here, this is 5. I will consider. This is 10. I will consider. It is 11. I will consider. It is 15. I will consider. This 20 I will consider. This is the temperature. X-axis is temperature. I am going to consider here. The y-axis is the resistance here. Now I will consider here 1, 2. Just a minute. Here 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 100 resistance I am going to consider here. Initially at temperature is 0, resistance is 0. I will consider for the nickel material. I will consider here. Okay. Otherwise I will consider a copper first only. First I will consider copper. Okay. So temperature here also I will consider 5, 10, 15, like that you use that one resistance. For the copper material, if the temperature increases 5 degrees Celsius, the resistance is also increasing 5 ohms here. Understood? The resistance is also increasing 5 ohms over there. I will consider here, that is 5 ohm here. 5 ohm, 5 degrees Celsius. Next, the temperature will increase 10. The resistance will also 10. For 15, the 10 resistance is also increasing here. So, how the temperature will increases, like that the resistance is also increasing here. So, the resistance is linearly increasing with temperature. We can say this. We can say the formula. Resistance is linearly. See here, जैसा resistance increase हो रहा है, temperature increasing, like that the resistance is increasing for copper material. So this one, it is linearly increasing here now. The resistance is increasing linearly with the temperature here now. We can say like this. Yes. Yes or no?
Sir.
Okay.
Yes, sir.
Consider which one I will consider. I will consider the nickel here. I will consider the nickel here now. The nickel, what will happen? For the small change in the temperature, there is a big change in the resistance here now. It is like this. The resistance temperature is very small change, but in the resistance, there is a big change here now. See here 0, here 0 is there. Only this much temperature change is there, but the double of that resistance is doubled here now. Yes or no? There is a small change in the resistance. There is, temperature. Then the big change in the resistance will occur here now. That is almost we can consider that is square of that value. It is going to change over there. Second condition, there is so much change in the resistance, temperature, but only small change in the resistance here. Three condition hai idhar. There are 3 conditions are there. One is if the temperature is changing, resistance is changing with temperature linearly here. I'll consider like temperature is increasing, how same like in the form of that the resistance is increasing here now. Resistance is increasing in linearly with temperature here now. That is one term. Second one, there is a small change in the temperature, but very big change in the resistance here now, like this here now. And third one, there is big change in the resistance, but there is no only very less change in the small change in the resistance here. There is bigger change in the temperature, but change in the resistance is very small here. Blue color line. That black color line, small change in the resistance, sorry, temperature, there is bigger change in the resistance, and the red color, the resistance is linearly changing with the temperature. समझ में आया क्या नहीं? बीच में मैंने रेजिस्टेंस टेम्परेचर का वर्ड मिस किया तो बोलो अभी. 3 conditions are there. So for the temperature here now, so temperature, first one, temperature increasing the resistance for the copper, it is linearly, it is increasing. For a temperature, how it is changing, like that the resistance will increases linearly. For the nickel material, only small change of the temperature is there, but there is a big change in the resistance. Big change in the resistance. For the platinum material, there is large change in the temperature, but the resistance is very small change in the resistance here. Small change in the resistance. These 3 conditions are applied for the platinum resistance temperature detector material here. Platinum resistance temperature detector material. Same thing I have written in here in this one here. In RTD devices, copper, nickel, and platinum are widely used metals here. These 3 metals we are going to use. These 3 metals are having different resistance variations with respect to the temperature variations here now. That is called resistance temperature characteristics. We are going to call that. This is characters. This is construction and working here now. Is it clear? The concept is clear, or if you have any doubts, you can ask. If you have any doubts, you can ask me. Yes?
No, sir.
No doubts? Okay. Then we'll go for the advantages and disadvantages. So we'll go now. Someone has written in the chat box. No, sir. Okay. So next part, we'll go for the advantages of the RTD, resistance temperature detector here. So it will give the accurate value. I told that one in the bridge, while doing the bridge circuit, only discussing the bridges, it will give the accurate values here. The bridges will give the accurate value. So here we are using a bridge method. So obviously the values are whatever the output or measurement is there, that is accurate only. The second advantage is resistance element, resistive element is there, can be used to measure differential transfer temperature here. Now you can different materials you can use the copper, you can use the nickel, you can use the platinum here. Now for the differential temperature you can use different materials here. Now that is the second advantage. Third one, extremely accurate temperature sensing here. If small change in the temperature, then the sensing element will change. Then immediately what will happen? The bridge will become unbalanced and it is going to detect here now. So extremely accurate for temperature sensing here now. No necessity of temperature compensation here. We are not no need to compensate that one. This temperature is high, we have to compensate like that. There is no necessity of any compensation over there. And stability of the performance over a long period of time here. Now it can, for long period of time, it will be stable, and stable operation it is going to give. So these are the some 5 advantages are there, advantages of the instrument. Okay. So if the instruments are there, means it has advantages and disadvantages. So these are the 5 advantages are there. From the observation, I will ask that one, is there any disadvantages? Common disadvantage, anyone, can you tell me any one disadvantage of the RTD? RTD, can you tell me? Accurate है, high performance है, stable है, these are the advantages. Disadvantages में क्या रहते हैं?
Cost is
Very good. Any equipment you consider, the cost orientation only we are going to do that one first. Everyone will tell that one. Apple phone is very how any features, big features and all the things. So many advantages they are going to tell. Why everyone is not using that Apple phone, then iPhone? Why those people are not using? Because of
Cost.
Or cost.
cost only. The main disadvantage of all the equipments, that is that it is not, people will not think about the performance, but that should be, what is that one, reasonably available to all the persons here now. So the cost is high. The cost is high because what? That is first one, high cost is there. This is first, high cost. Second one, it needs the bridge circuit here now. So bridge circuit ko power supply is required. Yes or no? We have to give the power supply. So that is the second disadvantage is there. Possibility of self-heating. We are using a bridge circuit and different resistances we are using. So if it is because of continuous running, the resistances or the kit, it is going to, the bridge circuit, it is going to heat itself here. So there is a possibility of self-heating is there. So these three are the disadvantages of the RTD here now. Disadvantages of the RTD here now. It completes the RTD here now. So related to RTD, we can ask any questions, you can ask me. If you have any doubts, any questions, you can ask related to RTD only. Before proceeding to the next topic, that is LVDT. RTD का कुछ डाउट है क्या? A division students तो चुपचाप बैठ के देखो. All of you are sitting silently. For you people, it is a repetition. Okay, if you don't have any doubts, then I will move forward to the LVDT. Yes. Okay. You people are not asking means I will assume that one if you don't have any doubts. So I will move towards the LVDT, that is called linear variable differential transformation. So in the LVDT, whatever the linear displacement is there, that one we are going to measure in the form of voltage. We are going to measure here. So the displacement we are going to measure in the voltage form here. Now the displacement is physical quantity and the voltage is electrical quantity. So any physical quantity is converting into electrical quantity. So that is called transducer, we are going to call that one. So linear variable, whatever the displacement is there, and differential transformer we are using here now. So the transformer, it is required electrical supply or not? Transformer को supply का जरूरत है क्या नहीं? Already you have studied the transformer. फर्स्ट ईयर में स्टडी हो गया, अभी मशीन में स्टडी किए हैं. नेसेसिटी है क्या पावर ट्रांसफार्मर को सप्लाई? यस और नो? How many windings are there in the transformer? Can anyone tell me? Single phase transformer I will consider. In a single phase transformer, how many windings will be there?
Two.
Two.
Windings. What are those windings?
Primary, secondary.
Primary, secondary here now. You are going to give input to the primary transformer or not?
Yes, sir.
Input, what type of input you are going to give?
Single phase.
That is electrical input only we are going to give. Na? So it requires the power supply. So you can say that one, it is not an active transducer, it is a passive transducer. Yes or no? So to convey that one, I have taken this many questions I have asked for that purpose only. So LVDT is a passive inductive transducer. It is nothing but it is works on the inductive principle here now, electromagnetic principle it is going to call that one here now. So it converts linear displacement into electrical voltage here. Whatever the linear displacement is there, it is going to convert into electric voltage, it is going to convert here. It consists one primary and two secondary windings here. Now I will show here only. Full explanation is not there here now, not required. See here, the shape of this one is here. See here, this is one primary winding we are going to call here now. This is primary winding. Both sides we have used the same shape only, but here I will consider as secondary winding this one, and this is secondary winding one. So secondary winding is split into two parts here. Secondary winding is split into two parts. It is split here. So EMF induced in the secondary winding we will consider as E1, and EMF induces in the secondary winding, that is called E2 here. So one primary winding and two secondary windings or coils it has here. It consists of one primary and two secondary coils are there here. This is one secondary coil and another secondary coil. This is one primary coils here. Now in between we have used one soft iron core we have used here now. Soft iron core we have used now, and we have provided one arm to that one. If this arm, it can push inside up to here and we can take back up to here. So based on this principle, if the iron core is pushed into inside that one displacement, right side of that one, so magnetic flux linkages will be more than this one. E2 will be EMF induces in the E2 will be more than E1 here. Now if it is pulled back here now, so the EMF induced in the secondary winding S1 will be more than E2, S2 here. Like that, based on this principle, it is going to operate here. It is going to operate. This one complete this shape whatever we are using here now. This is core material, iron core we have used here. This is the core material only, all the thing. This one is core, and here arm soft iron core is placed in between that two windings here. In between two windings we have placed that one. So working directly, it has three positions, based on three positions it is going to operate that one, the working of the LVDT here now. See here, this is outer look of the diagram. Now I'll go to the inside of that one here. Now here one primary coil is there. Are we visible? See here, this is
Yes,
one
sir.
primary winding is there. This is two secondary windings, secondary winding S1 and secondary winding S2 here now. So EMF induced in the S1, that is called E1 we are going to call, and EMF induced in the S2, that is called E2 we are going to call that one. So these two are the secondary winding. We are going to connect to each other here now. So the net output voltage we are going to consider as here E1 minus E2 here. E1 minus E2 we are going to consider here. Understood? The output voltage, total EMF induced is E1 minus E2 here. We are going to consider here. Okay. So what we will do, at initial condition, this iron core is there. Which one? We are going to move that one here. We are not going to move here now. We'll place at center here now. Center part will place this moving iron core here. Soft iron core is there. That one we have placed at center here now. So the magnetic field produced here in between these two coils, it will be equally connected to the secondary winding coil 1, S1 and S2 here. So the flux lines are connected equally to the S1 and S2. Then EMF induced in the S1 is equal to S2. Equally it is connected means E1 equal to E2 only, na? Yes or no? Flux linking is equal, then EMF induced in the coil S1 is equal to the EMF induced in the coil S2. So on that condition, E1 equal to E2 we are going to consider. So the total output voltage, that is called E1 minus E2 equal to E1 minus E2 equal to what? नवी नहीं बोल सकते. E1 equal to E2. Whatever the E1 induced EMF in the coil S1 is there, that is equal to EMF induced in the coil S2. So E1 equal to E2 is there. Tell me the output value, output voltage equal to, we know the formula is E1 minus E2. Anyone, can you tell the formula, what is the value output voltage we are going to get here now? Yes?
0.
0? Who is that saying 0? कौन बोला है 0 बोल के? कौन है वो? रोल नंबर, roll number, who has told 0? That is the correct answer. Very good. The output voltage is 0 because E1 minus E2 is there. So in the place of this E1, you substitute this one as E2. E2 minus E2 equal to? E2 minus E2 equal to what?
0.
0 only, na? Simple question is there, simple answer is there here. So if the output voltage is 0, then that position we are going to call as null position. We are going to call that one as. That is called null position. It is going to operate in 3 positions. One null position, left position, right position. We are going to call that one. At null position, the output will be 0. The output will be 0 over there. Okay, is it clear? Second one, suppose instead of this one at center, I will take this one into here now. I will shift into left side now. I will shift into left side. The iron core pieces I will use here now. So because of this, the maximum flux linkage will be there for the S1 only. The maximum flux linkage will be there for the S1 only. So E1 minus E2 formula we are going to use again here now. So maximum flux linkage to the S1 only means EMF induced in the S1 is greater than EMF induced in the S2. E1 is greater than E2 or E2 is greater than E1?
E1 greater than E2.
E1 is greater than E2. For the left position, E1 is greater than E2. So the answer will be in positive or negative now?
Positive.
Answer will be positive because E1 minus E2 we are using the formula. We are going to get the positive answer. That is called left position. We are going to call that one. Same thing we are going to use for the same formula, same principle. Suppose instead of shifting into the left, I will push this coil, whatever the iron core is there, I will into right side of the that one. So the maximum flux linkage will be there for the S2 now here. It will be there S2 here now. On that condition, E2 is greater than E1. E2 is greater than E1. Then on that condition, what is the output voltage? Positive or negative?
Negative.
The formula is E1 minus E2 is there. So the output voltage is negative here now. So for the negative, we are going to get that is negative for the E2 is greater than E1. For the right position, we are going to call that. So like this, there are 3 positions are there in the operation. 3 positions are there in the operation here now. Null position, left position, right position here. So when the primary winding is excited, when the primary winding we are going to give the AC power supply here now by AC current, it produces a alternating magnetic field will be produces. This alternating magnetic field induces voltage in both secondary windings depending upon the position of the core in the hollow former. Depending on the core in the former, whatever this one here now, if it is center, then equally it is going to link the flux linkages. It is going to field the produces the magnetic field here. So the output at secondary in coil S1 is E1. In the coil S1, secondary coil S1, whatever the EMF will induces, that is called E1 we are going to consider. S2, that is called E2 here now. So the differential output, linear variable, we are varying this one here now, and differential output we are going to get the differential output, that is called E out equal to E1 minus E2 we are going to consider. So this is the general step. Rule number 4 abhi join ho gaye, fir bhi I will put absent. Okay, so the null position, when the core is at null position, this core is at center is there here now. See here, center is there. So the flux linkage here also some turns only it is linked, here also some turns only it is linked here now. When the core is at null position means for no displacement, it is not at left, not at right here now. At center it is there here now. So at null position, then the flux linking with both the secondary winding is equal to the induced EMF is equal here now. Flux linkage is equal to the both the secondary windings. On that condition, the EMF induced in the secondary S1 is equal to EMF induced in the secondary coil S2. That is nothing but E1 equal to E2 we are going to call here now. So equal. So the induced EMF is equal in both the winding. So for no displacement, the value of output is 0. E1 minus E2, the differential output is E1 minus E2. So there is no displacement and the EMF induced in both the secondary coils is equal. Then E1 equal to E2. Then output is 0 here now, as E1 and E2 both are equal. So it shows that no displacement took place here. E1 minus equal to E2. So E out equal to 0. Is there any displacement? No. Initial value only we are, whatever the iron core position is there, that is standard at 0 is there. So that is called null position. We are going to call that. This is called null position. So left position is there here. So whatever the core is there, I have taken into left position here. Now I have done a movement of this one here now. So the maximum flux linkage is there at the secondary coil S1 only. The maximum flux linkage is there at secondary coil S1 only here now. So EMF induced in the coil S1, that is called E1, is greater than E2. E1 is greater than E2. And that condition we are going to consider as positive output we are going to get here now. When the core is moved to left of null position. Null position means center. Left of the null position, we have shifted the core here now. In this case, the flux linking with secondary winding S1 is more as compared to the flux linking with the S2. See here, the red line, kidhar link ho gaye zyada? All are linked to the S1 only. There is no linking at S2 here now. So due to this, E1 will be more as that of E2 here now. EMF induced in S1 is greater than S2 here now. So E1 is greater than S2 we are going to call. So due to this, we know the formula, the differential output is E1 minus E2. So the output is positive here now, left of null position here. If it is shifted into left, that is called, what we are going to call that is positive output we are going to get here now. Some people similarly, समझ में आ रहा है क्या नहीं?
Yes, sir.
Similarly, we will consider the right of the null position here now. Instead of this left position, this core I will shift into right side here now. I will shift into right side. So maximum flux linkage will be there for the S2 coil only, secondary coil S2 here now. So flux linkage is more here, then EMF induced here now will be more as compared to S1 here now. So E2 is greater than E1. On that condition, we are using the formula that E1 minus E2. So E2 is greater. So suppose any value you are going to consider, suppose 2 minus 4. What is the answer here now? 2 minus 4. What is the answer you are going to write?
-2.
-2. So answer will be in minus. 4 minus 2. What is the answer?
2.
Minus 2.
2.
2 is the answer. So the bigger value sign we are going to consider for this one here now. So for the bigger value, it is plus is there, +2. Here E2 is greater than E1. So the answer will become, the differential output is in the minus is there. So that is called negative here now. So for the right of the null position, we'll get the negative output, and left of the null position will get the positive output. If it is, there is no movement at all, the displacement moment displacement is 0, on that condition, that is the output will be 0. So that position we are going to call as null position. We are going to call that. That is called null position. So this completes this is the working principle, working of the LVDT here. Working of LVDT here. So this outputs and these all the things. We'll see that one. समझ में आया? This is the working. Null position means there is no displacement at all. Left position means we have taken left side. The core is taken into left side, and right position means the core is moved into right side here now. So based on that, the flux linkage will be changes from primary to secondary here now. So based on the flux linkage, EMF induced in the secondary windings will change. According to that, the differential output will changes 0, positive, negative we are going to get here now. So based on that, we are getting the answer here. If it is we are getting the answer positive, then we can say that one it is at the left side. If it is for negative, we can say that one that is under right side here. How much value we are going to get, according to that we can identify the displacement here. Okay, anything else? So see here, this is the graph, actually output characteristics or output voltage we are going to call. At null position, the output is 0 here. At null position, the output is 0 here now. But if it is left side, slowly it is in the right side now. Displacement will be left now. Okay, left is there, then the positive output we are going to get here. Where is the positive? This side we have to get, but we are not getting here now. Displacement right side, left side, that is mirror copy, it is going to increase over there. So in phase, and after that some value here, it is going away, that one here now. This part we'll discuss in the tomorrow. I will discuss this part here. Why it is going away, what is the linear range of that one here now. So why it is positive and negative, we'll discuss in the next class. We'll discuss this output voltage versus displacement, we will discuss in the next class, as well as some advantages of LVDT is there, disadvantages are there, I will tell in the next class. There is no written I have anything, so that's by seeing this diagram only will take another 10 minutes to explain. So only time left is 2 minutes. Just a minute, I am not taking the A division attendance. Roll number 7, are you there? Roll number 3. 11, 15, 14, 17, 19, 21, 24, 25, 26, 29, 31, 36, 37. These are the absent numbers for the today class. Roll number 6 is joining now, so already has joined. So we'll stop here only and we'll continue in the next class. समझ में आ रहा है क्या सबको?
Yes, sir.
Topic is very easy. Transducer part is very easy actually. Little bit difficulties will arise in the instrument transformer, and only instrument transformer part has some derivation part. Other things again the theory part is there complete. Okay, so already 6 experiments are over. You complete the write-up for that one. Tomorrow you have the practical. So another 2 practicals will complete maybe in tomorrow or next week. Okay, so we'll stop here only.